Okay, good morning, everyone. I'd like to thank the organizers, Suman and Abi and the others, for inviting me to be here. It's a pleasure to visit this place, very contemplative place, I think. But it's nice to have an early summer, let's say, coming from Northern Hemisphere. So I'm Garrelt Mellema from Stockholm, and I'll be talking about looking at the intergalactic medium using 21 centimeter observations. So I thought I could start with a little metaphor. So reionization could be seen as a crime, right? So there's a victim, the intergalactic medium, and there are culprits. They live in galaxies. We don't really know who they are, actually. And we're trying to solve that crime. Now, apart, if you watch this detective series, an important element in solving the crime is to do a proper post-mortem of the victim, in this case, the intergalactic medium. So I'll be arguing that we should be trying to do that with 21 centimeter observations. So this is part of the work within the LOFAR EOR project, the interpretation, the theory team. So with contributions from Raghu, who's here in the audience, my former PhD student, Ivo Georgiev, and Sambit, Giri, Benedetta Chardi, and Salim Zaroubi. So I'll start with the introduction on the 21 centimeter signal, connection to the sources and the IGM. And then I'll describe a IGM framework that we developed for the 21 centimeter power spectrum, and to continue on what that framework means in terms of the physics, and end with summary and conclusions. So normally when we do a simulation of the, to produce a model of the 21 centimeter signal at various redshift, we produce in the end this the signal, and for that we need the neutral fraction, the spin temperature, and the density field. The density field is given by the cosmology, and it's an evolving quantity. So this is, the evolution here is driven entirely by the cosmological evolution, gravity, and expansion of the universe. The neutral fraction, the spin temperature, are caused by the sources of radiation driving these processes. And those are assumed to live in halos, and then we describe with parameters and models how the star formation works inside those halos, and how photons possibly get out, the escape fraction, so an interstellar medium effect here. And of course, feeding into that is how many halos do we have of a certain mass, which again is given by the cosmology and is an evolving quantity. These quantities can be evolving. In many models, they're often taken to be constant because, yeah, how well do we know this? If this is then given by sort of galaxy evolution models. Now, the nice thing about modeling this is that the evolution is built in, right? So this is evolving, cosmology evolving, the halo mass function is evolving, possibly this recipe has some redshift dependent. And so you get an evolving structure, and it means that if you know in your model, you can, you know it at one redshift, you also know it at another. And then if you have a model like this, you can do inference on the parameters, which are essentially, if you trust your cosmology, most of the important parameters are the star formation related parameters and the ISM parameters, so star formation rate and escape fraction, etc. Now, when you measure the 21 centimeter signal, though, you're not measuring star formation rates or escape fractions. You're measuring the structure of the intergalactic medium. Neutral fraction, bubble sizes, etc. That's what sets the 21 centimeter signal. So it directly depends on the IGM properties and not on only indirectly on the source properties. They caused it, but they're not setting those the numbers. And so when we interpreted the LOFAR upper limits in 2020, we actually tried to provide constraints on the IGM parameters. And Jordan Mirocha in 2022 also proposed a scheme for doing that. And I'm not going to talk about that. I think Raghu will talk about the interpretation, so you'll have to wait a little bit for that. But what I want to talk about is, I guess there are two issues here. We saw already in Andrei's talk, some of the priors can get quite complicated. That's an issue when you want to do this. But actually, the big problem that we have been discussing more recently within LOFAR-UR is like, how do we handle multi-redshift data? Here, this was a single redshift. And the point is that through the source parameters, you have these connections between the redshift. But if you now say, no, I want to know the mean ionization fraction, the bubble size distribution, etc., these are kind of instant properties that are not necessarily connected between redshifts in your model, let's say. So in order to make some progress there, we worked on trying to develop an evolution model for the IGM parameters, which should be sort of universal enough that it fits many different source models. And in last year, we published a paper where we presented this 8-parameter universal model for the case of only where there's no, the spin temperature has become unimportant, it's saturated. And this was based on 24 Grizzly simulations. And the key quantity in this evolving model is the so-called 21 centimeter bias, the scale-dependent bias. So the ratio between the 21 centimeter power spectrum and the matter power spectrum. And now, why the 21 centimeter bias? It turns out that when you look at the shape of the bias, a scale-dependent bias, there's a bunch of them here, it follows a relatively simple shape compared to the raw 21 centimeter power spectrum. There are two clear regimes. So early on, when the neutral fraction is higher than a certain minimum fraction, this typically 80%, 90%, it's a single rising power law is a good description of the bias function. And after that point, it sort of transitions into a more complex shape, which during at least some is a double power law. You can see an example here. Here, it's actually the double power law is transitioned into a single falling power law. And so anyway, this allows us to fit the bias essentially with 3 parameters. So here we have written this 21 centimeter power spectrum, but here's the matter power spectrum. So the bias is this A, and then these 2 power laws for the later regime and the single power law for the early regime. So now we need to find the evolution. Though, if you look, for example, at this amplitude that was in there, this A, you see that for all the models, we have this up and down kind of prescription, which can then, where it goes down to a minimum, and this is actually the transition point between the 2 fits, and then up to a maximum and down. And this can be parameterized. As you see, this is a function of the neutral fraction, so we can parameterize it as a function of the neutral fraction, which means that for our time dependence, knowing the redshift dependence of A, we need a parameterized reionization history, and we use this function here, which has 3 parameters around the central. There's a central, the 50% point, there's a width, but there's also an asymmetry built in here. So in the end, we end up with this framework, which is 3 parameters for the reionization history and 5 parameters for the evolution of A and this power law index gamma. So they're here, so you can see the 3 reionization history parameters, and the 5 21 centimeter bias parameters. Now, I guess the rest of the talk will be that what these mean is quite clear, but these ones are at some level a bit mysterious because they're just numbers. So let's say we do an inference on these quantities, we get answers here, and then this is nice, we get the reionization history directly from the 21 centimeter power spectrum, but then we get constraints on these parameters, but what do they really mean? But before we get there, we can show that it actually works, or at least easily works well. We took a radiative transfer simulation with C2 ray, extracted the 21 centimeter power spectrum from it, and then reconstructed these parameters using the framework. Remember, the framework was developed with the Grizzly simulation, so in principle, there's no connection between these two. And then we could actually reproduce the correct reionization history using that framework. You can also see that when you look at the posteriors for the various parameters, there's some degeneracies in there actually, which suggests that this framework is probably not the final answer. We can still develop it a bit more. Of course, it does not include the spin temperature fluctuations, which is so this we'll have to work on, expand it to do that. Maybe the fits are not optimal yet. We'll be looking at that. But as I already hinted at, we're also interested in saying, okay, what can we do with these numbers? What is the physics behind it? And so this means that we have to go back to this quantity, the 21 centimeter bias, and sort of try to understand it. So here's a plot with a whole bunch of 21 centimeter bias curves from various models, 21 centimeter fast models. And then what is noticeable here is, and these are all for the later stages, so beyond this minimum, where we use the 2 power laws to characterize this. And so what you see here is that it seems to have a fairly consistent shape of a roughly constant, let's call it then a linear large-scale bias, which we'll call B0, and then a turnover at some scale, different scales, and then a power law fall-off beyond that. And this transition is sometimes seen to be quite sharp, and sometimes it's a smooth transition. Now, of course, this is a quantity that has quite a bit of history. Already going back to 2004, there was attempts to understand this. Analytical model by Steve Ferlanetto on bubble sizes, etc., which in the end led to the excursion set model that is underlying 21 centimeter fast and the other semi-numerical codes. Actually, that paper shows what the 21 centimeter bias shapes are for that model. And so you see at some level it goes flat for very large scales. It has this sort of fall-off, possibly power law fall-off for small scales. This is the K value, this is the bias. But then it has these maxima between it, which we never see in the simulation. Maybe not so surprising, it's known that this model doesn't perfectly describe the evolution of bubbles. There is an alternative description by Paranjape and Tirthankar that could be interesting to see if it does better in this respect. Anyway, because we don't have a theoretical analytical understanding of this, we've been looking, basically taking the path of doing many simulations and trying to find correlations between the features and the values that we see in the bias curves and the physical parameters. And so here's a good example, and this was actually something that we saw even before we were developing this framework. If you have these older 21 centimeter fast models with a hard barrier on the extent of source influence called R max, you actually see quite clearly that early on, the transition scale, where this sort of turns over, has a value which is larger than 2 over R max, and it's more smooth. But then as reionization progresses, it sort of moves to K-trans gets stuck at a value of 2 over R max, and also becomes quite sharp. So here are some examples. Different simulations with different values of R max, 10, 20, 40, 70 megaparsec, and then the vertical lines indicate 2 over R max for the different colors, so the blue, the green, different simulations, and you see that those transition scales match that exactly. And so this suggests that actually this transition scale, this K-trans, measures the effective mean free path of ionizing photons, initially set by the distribution of bubbles, but then when the bubbles become too large, it's actually set by the absorption inside the bubbles, which is, in this model, is given by this R max parameter. Another physical quantity, and this actually comes from the Fernletto work and also later work by Matt McQuinn and Hansen D'Aloisio, that suggests that the source bias or the halo bias, I guess our sources are halos, is also a quantity that comes in. So here we see 3 21 centimeter fast models where we plot the halo bias. There are 3 different, they have 3 different minimum masses. So 10 to the 8, 10 to the 9, 10 to the 10. Everything else is identical in those simulations. If you then plot the halo bias against the neutral fraction, so the reionization, so it starts here, fully neutral, and then it goes to fully ionized, well, 50%, sorry, here. You see actually that those 3 simulations have a nearly identical halo bias neutral fraction relation. Let's take 60% here, right? So these 60% in these 60% neutrals or 40% ionized, it happens at different redshifts in these 3 simulations. Because in the 10 to the 10 solar mass, minimum mass, you have very many fewer sources than in the 10 to the 8. But they all happen when the halos that are driving the reionization have a bias of a little bit less than 4. So there seems to be this connection. And in fact, you can do a larger sample of models, and you see that this connection exists. So there's neutral fraction halo bias. It doesn't depend on minimum mass. It does, though, depend on your source efficiency, which is parameterized here with this zeta. You have different halo mass, halo bias neutral fraction relations for different values of the zeta. And here, this is the redshift. Right. So this is just a connection between reionization history and halo bias. So what about the connection to the 21 centimeter bias? So we looked at the large scale bias is B0, where it's linear. And here again, we look at those 3 models with 10 to the 9, to 10 to the 8, 10 to the 9, 10 to the 10. And you see around 55%, the bias curves, the large scale bias is identical between those 3 models. And then it differs for the small scale bias. So this sort of suggests maybe there is actually a B0, BH relation. However, if you then follow this trajectory for later lower values of the neutral fraction, so we looked at 55, which is here, then there were, the B0 was identical. You actually see that they diverge for lower values. So it's not a single relation. You do see here is the halo bias neutral fraction relation, which is identical for these 3 right to the end of reionization. So we're speculating that actually that it starts to change is because there is more overlap between the ionized bubbles created by the individual sources. And the more overlap creates a higher amplitude. These are negative values. So this is the one with many sources, and so more overlap. Another quantity then to consider is the mean free path. We already saw the connection to the transition scale. So is there a connection to this large-scale linear bias? And so here is a similar plot, 3 models, one with everything's identical except the mean free path is R max. Here it's 10, 20, and 70. Again, you see this is the curve that shows the halo bias against the neutral fraction. This curve shows the redshift. Here is the value of B0. And so what you see is, again, it's sort of similar up to a point, 70% neutral, and then it starts to diverge. But actually, the divergence supports this correlation, so it supports this hypothesis about this correlation between overlap and B0, as this is the one with the largest negative value of B0 is the one with the largest mean free path, so that it will enable more overlap between bubbles. Right. So these are just some clues, essentially, that we picked up from doing working with this large sample of reionization models and exploring these multiple-dimensional correlations. And this is still very much work in progress, so we haven't figured it out completely. No, it's a complex autopsy, let us say. So I'll leave it at that, actually, slightly early. We can get to coffee early. So when you do parameter inference on 21 centimeter observations, you can do it on the source parameters. This comes most naturally from the way we model the 21 centimeter signal simulated, and it may be also what you ultimately want to know, who did it. But then again, we should not forget the autopsy and properly understand what the structure of the IGM. The current methodology for IGM parameters is really a per redshift methodology, so it doesn't naturally connect the IGM parameters between redshifts, and so we've been looking at a way to make that connection, and then it seems that a framework around the 21 centimeter bias seems to give us this parameterizable evolution of the 21 centimeter power spectrum that can be used to connect directly to the IGM properties. And we've seen that the shape of the 21 centimeter bias curves connect to some of the key physics, like the mean free path, the halo bias, and the neutral fraction, but we haven't uncovered the whole picture yet. Okay, thank you very much.
Questions? Okay, is it okay? Yeah. Among the parameters describing the bias, probably the easiest to understand would be the B0, the large scale constant bias. Now, what I remember is in the absence of inhomogeneous recombinations, that is exactly equal to the efficiency weighted halo bias. I mean, you can probably analytically show that. So I guess if you put Rmax to infinity to a large value, you should be able to recover this. I mean, have you tried this? And then you can see what is the effect of inhomogeneous recombinations on this.
Right. So essentially, take this one. You're saying that it's this lowest curve should have a simple solution. Yeah, this one is the largest between these three. Okay, but it does have recombinations here. So, removing the recombinations. Okay, well, that's a good, I wasn't aware of that result.
More questions?
Going first, going second.
Let's go for coffee then.
Okay, so let's thank the speaker again and all the speakers in the morning session.